Hi, everybody. It's Professor Mitchell. Today we're looking at section 7.3 on exponential functions. Now, in the last section, I said that it was going to be a two-part video and ended up being a three-part video. So I will just say that this one will be at least two parts. All right. I try not to make them super long. And then that way it's easier to break them up, watch one in the morning, one in the afternoon, or one on Tuesday, one on Wednesday, whatever. All right. So I want to spend just a little bit of time talking about the inverse of natural log x and the number e. So as a definition, the inverse of the function y equals natural log x can be written like this: y equals inverse natural log x, except that's not usually how we write it. And at the beginning, when I first define this function, I like to write it like this: y equals exp of x, exp for exponential. All right. Now, you may remember from your pre-calculus class that this function goes by a different name. But I want to build a little bit of suspense, and I'll explain why in just a second. All right, so here you see the graph of y equals natural log of x, and using the business about the graph of an inverse function is found by reflecting the graph of the original function across the line y equals x. We find that the graph of y equals exp of x should look something like this. And then recall from the last section that e is the number satisfying natural log of e equals 1. So because exp of x is the inverse function of natural log x, that means that e is equal to exp of 1. All right, so now we're going to get our big surprise ending here. And ordinarily, I would spend a little bit more time on this, but I'm trying to be good. Like I've said in the last couple sections, trying to respect the fact that not all of you are math majors. So anyway, this will give you the idea if you're interested. For R rational, it turns out this is true for real numbers R, all real numbers are. But if I had to prove it to you at this point, I would only be able to prove it for rational values of R. Look at the natural log of e to the R, which by my favorite power property of logarithms becomes R times natural log e, which is equal to R. So then if you apply inverse natural log to both sides of this equation, you get e to the r equals exp of r. So this is what I was referencing a minute ago. You probably have never seen this notation before, but I like to spend a little bit of time developing this because really there is no good there is a good reason that the inverse function of natural log x is raising the number e to a power. All right, so by originally calling it by this name, I'm showing you that there's a good reason it ends up being raising the number e to the power x. Okay, all right. So for every real number x, we define the natural exponential function to be e to the x equals exp of x. In other words, the inverse of the natural log function. Here are some typical values of e to the x. One big takeaway from this, look at what happens when you increase the value of x from 1 to 2, and then from 2 to 10, and then from 10 to 100. The value of e to the x just absolutely blows up. So you've probably heard the term exponential growth. When something grows very, very fast. And this is where that comes from. All right, so since e to the x and natural log x are inverse functions, they have to satisfy these properties that e to the power ln of x is equal to x. And that's true for all x greater than 0, because x greater than 0 is the domain of the natural log function. For all values of x, natural log of e to the x is just x. All right, so that brings us to some laws of exponents. I am not going to prove these to you. I'm going to resist the urge. For all numbers x, x1, and x2, the natural exponential function e to the x obeys the following laws. E to the power x1 times e to the power x2 is equal to e to the power x1 plus x2. E to the x1 divided by e to the x2 is equal to e to the power x1 minus x2. E to the power opposite x is the reciprocal of e to the x. And then finally, e to the x1 raised to the power r is equal to e to the power r times x1. And again, we have to put a note on that that says if r is rational. It turns out this is true for any real number r. We just can't prove it yet. All right, so that brings us to our first example, and I am going to switch over to the tablet. All right, so remember the instructions were solve for t. Our first equation says e to the power negative 0.01t is equal to 1,000. So basically, and you may remember this from pre-calc, what you want to do whenever the variable that you're trying to solve for is in an exponent, that you should apply a logarithm to both sides. So we will apply natural logarithm to both sides. And that's going to give us natural log e to the negative 0.01t equals natural log 1,000. By the inverse property of natural log x and e to the x, natural log of e to the negative 0.01t is just negative 0.01t. All right, so suddenly we're looking at an algebra 1 equation. We will divide both sides by negative 0.01. And we find that t is equal to negative natural log 1,000 divided by 0.01, or it looks a little bit nicer if you write it as negative 100 times natural log 1,000, right? All right, so that was pretty easy. Let's look at letter B. E to the power natural log 2 times t is equal to 1/2. So again, the variable is in an exponent. We should apply natural log to both sides. So natural log, natural log. We have natural log e to the power natural log 2 times t equals natural log 1/2. By that inverse property of natural log x and e to the x, natural log of e to the power natural log 2 times t is just natural log 2 times t. All right, so now if we divide both sides by natural log 2, we get t equals natural log 1/2 divided by natural log 2. Now, is it possible to pretty that up? Well, yes, it is, as it turns out. So if you think back to the last section, there was a property of natural logs that said that the natural log of 1 over x is equal to negative natural log x. So using that property, we can rewrite natural log 1/2 as negative natural log 2. So guess what? It turns out that the value of t in this equation is just negative 1. All right, and finally, e to the power x squared times e to the power 2x plus 1 is equal to e to the t. Now remember, the direction said solve for t, and this equation also has x in it. So solve for t means write t as a function of x, okay? So the first thing I'm going to do is I'm going to combine those two exponentials on the left side. So that's going to say e to the power, remember this property, x squared plus 2x plus 1. All right, and now you could take natural log of both sides, but I'm not going to write that down because I think you can see what would happen. If you take natural log of both sides, you will just end up with x squared plus 2x plus 1 equals t. So that's it. The directions were solved for t, and it turns out that t is just x squared plus 2x plus 1. Done. All right, back to the presentation. Okay, here's the moment I've been waiting for. Got to bring calculus into it sometime. So this is about the derivative and integral of e to the x. If u is any differentiable function of x, then the derivative with respect to x of e to the u is just e to the u times du dx. All right, this is huge. I probably should have put just the regular version of this equation in here. I tend to put the chain rule version because that's the more useful version. But what this says is that e to the x is its own derivative. And that makes e to the x one of the most useful functions in all of calculus. All right. We have a lot of use for a function that is its own derivative. Okay. Now, this is one of those things that I absolutely cannot resist proving to you. All right. It's very easy to prove. So let me go back to my tablet. And I'll just prove the regular version, which is right here, says that the derivative with respect to x of e to the x is just e to the x. All right, so I'll write proof. Take y equals e to the x. We're trying to show that dy dx is equal to e to the x. And to do that, I'm going to rewrite this equation as x equals natural log y. Remember that e to the x and natural log x are inverses. Okay, so these two equations are equivalent. And now I'm going to take that second equation and I am going to differentiate it implicitly. I'm going to take the derivative with respect to x of both sides. All right, so on the one side, that's going to give me 1. The derivative of x with respect to x is just 1. And as we learned in the last section, the derivative with respect to x of natural log y is 1 over y times dy dx. All right, so let's solve this equation for dy dx. We'll multiply both sides by y. And that tells me that dy dx is equal to y. What is the last step of implicit differentiation? You have to, if possible, write the derivative in terms of x. That's not always possible, but in this case it is, because what is y? Y is e to the x. Isn't that cool? We started with y equals e to the x, and we found that dy dx is e to the x. All right. So e to the x is its own derivative. All right, and I think we're going to be using that in the next example, which is right here. We're going to differentiate each of these functions. I think there are 3 of them. Yes, there are. All right, so back to the tablet. All right, here we go. Y equals 1 plus 2x times e to the negative 2x. And we want to find dy dx. So here we're going to be using the product rule. So if you think of this as f, think of this as g. The derivative is going to be the first times the derivative of the second plus the derivative of the first times the second. All right, so f is 1 plus 2x. All right, now what is the derivative of g? That's the new toy, right? The derivative of e to the negative 2x is I'm going to write this in a different color just so it stands out, is e to the negative 2x times the derivative of negative 2x, which is negative 2. Okay. So here is your f. Here is your g prime. The other part of it's simpler. F prime is the derivative of 1 plus 2x, which is just 2. And then leave g alone, e to the negative 2x. All right, so we end up with negative 2 e to the negative 2x times 1 plus 2x plus 2e to the negative 2x. Now I'm noticing something. If you distribute that negative 2e to the negative 2x, we can definitely pretty this up a lot, right? Because you're going to get negative 2e to the negative 2x. The next term will be negative 4x e to the negative 2x. And then you'll have a plus 2e to the negative 2x. And these two terms cancel each other out. And it turns out that the derivative of this function is just negative 4x e to the negative 2x. So sometimes it does pay to pretty these things up. All right, next. Y equals the natural log of 2e to the negative t sine t. All right, so the instructions said differentiate, so that means this time we're looking for dy dt. All right, so first we're going to use the derivative rule for natural log. The derivative of natural log u is 1 over u times the derivative of u, right? So maybe that's worth writing down. The derivative, I feel a sneeze. Oh, it got stuck. Don't you hate that? Derivative with respect to t of e to the u. I'm sorry, that's not the rule I want here. Natural log u. Come on now. Is 1 over u times du dt. All right, so in this case, that's going to be 1 over 2e to the negative t sine t. And then we have to multiply by the derivative of 2e to the negative t sine t. You know what? Let's just write it like this. Okay, so to do that derivative, we need the product rule again, right? And would it be okay? I almost did this a second ago, and then I decided I should show more work. Really, I can just put that derivative in the numerator of this fraction, can't I? Okay. So I'm still thinking of this as f. I'm still thinking of this as g, but this time maybe I won't write fg prime plus f prime g, okay? I will just talk it out. So we have the first times the derivative of the second. The derivative of sine t is cosine t plus the derivative of the first. What is the derivative of 2e to the negative t? Well, it would be 2e to the negative t times the derivative of negative t, which is -1. And so that makes a minus here. That's why I left that blank. I kind of saw that coming. Times g, which is sine t. All right, so there you go. You could leave it like that. Or the other thing you could do is you could break this into two separate fractions. The first term would be, I'm going to write or because, you know, it would be fine to leave it like you see it there. Or if you split it into two separate fractions, you would have 2e to the negative t cosine t divided by 2e to the negative t sine t, and that would just give you cotangent t minus, oh no, I definitely like this answer better. 2e to the negative t sine t divided by 2e to the negative t sine t. That would just be 1. All right. Yeah, I like that answer better. Okay, let's leave it like that. All right. And then finally, I'm happy we get to do one of these. Y equals the integral of e to the power 4 square root of x to e to the 2x of natural log t dt. So this is one of those integral functions. You had, I think, a couple of these in the Calc 1 review quiz. This is a function of x. So what we're looking for is dy dx. Now, before I start messing around with dy dx, I want to point out to you that this integral can be broken into two parts, and we're going to need that in order to differentiate it. So let's make the first integral go from e to the 4 square root of x to, oh, it really doesn't matter to what number. Why don't we say to 1 natural log x t dt plus the integral 1 to e to the negative to the 2x natural log t dt. All right, and then I'm going to do one more thing. Instead of writing integral from e to the 4 square root of x to 1, I am going to switch it around, make it 1 to e to the 4 square root of x, and I'm going to put a minus sign. This will make it easier to differentiate. Okay, so let's put that on the back burner for a second. Okay, so part 1 of the fundamental theorem of calculus talks about differentiating this kind of integral function. It basically says that the derivative and the integral cancel each other out. What it says specifically is that when you have an integral from a constant a to a function g of x, and then, darn it, here you have f of t dt, and you want to differentiate that thing with respect to x. The chain rule version of fundamental theorem of calculus part 1 says that that derivative is just f of g of x, and then you just have to multiply by the derivative of g of x. Okay. All right, so back to the one we were looking at. It's right there. I'm probably going to have to flip back to this a couple of times. Dy dx for the function that we're working with Okay, so first we'll take this term here. So that's going to be negative natural log e to the 4 square root of x. Negative natural log e to the 4 square root of x. And then I have to multiply by the derivative of e to the 4 square root of x. Let's write that out. Derivative of e to the 4 square root of x. Okay. And then, so we'll deal with that in a minute. Now let's talk about the other term, the second term, this one right here. So the derivative of that integral function would be the natural log of e to the 2x times the derivative of e to the 2x. So natural log e to the 2x times the derivative of e to the 2x. Okay, it's a little confusing, I know. All right, so here's what we have. Natural log of e to the 4 square root of x, that's just going to be 4 square root of x, isn't it? This right here is going to simplify down to 4 square root of x. So we have negative 4 square root of x. The derivative of e to the 4 square root of x is e to the 4 square root of x times the derivative of 4 square root of x. And I think I better just write that down. And while I'm at it, instead of writing 4 square root of x, let's write it as 4x to the power 1/2. Okay. So we'll come back to that in a second. And then for this other term, the natural log of e to the 2x is just 2x. The derivative of e to the 2x is e to the 2x times the derivative of 2x. All right, so about one more step, I think I'll have the answer. I did not leave myself another blank screen, so let's just maybe get rid of this. All right, here we go. Okay, so we have negative 4 square root of x times e to the 4 square root of x times the derivative of 4x to the 1/2. So the derivative of 4x to the 1/2 is 4 times 1/2 x to the negative 1/2. Okay. And then this other term is going to be 2x times e to the 2x. And of course, the derivative of 2x is just 2. All right, so I think we can pretty this up just a little bit. Let's get rid of this. Because what do we have? We have negative 4 square root of x times e to the 4 square root of x. And then this here is just 2 over the square root of x, isn't it? X to the power negative 1/2 is 1 over the square root of x. So I want to do that because now that'll get rid of this and this. Okay. This, of course, is just going to turn into 4x e to the 2x. So my final answer is going to be negative 8 e to the 4 square root of x plus 4x e to the 2x. Wasn't that fun?